Welcome, everyone. Today, we're diving into the fascinating world of quadratic equations. The title of our presentation is Quadratic Equations, and we might have a subtitle as well. In this session, I'll walk you through what quadratic equations are, how to solve them, and why they matter. So, let's get started and explore this important topic together. Now, let's move on to some additional examples that will help us understand the concepts better. In this part, we'll explore the nature of roots, which tells us about the solutions of quadratic equations, whether they are real or complex, and how many solutions we might expect. Next, we'll look at solving quadratic equations using the quadratic formula, a very powerful method that works regardless of whether the roots are real or complex. Following that, we'll examine how to solve quadratic equations by factorization, which is often quicker when the equation factors nicely. We'll also discuss the discriminant, which is a key part of the quadratic formula that helps us determine the nature of the roots before actually solving the equation. Additionally, we'll review some more examples and practical applications to see how these methods are used in real-world situations. All of these topics tie back to understanding the overall structure of quadratic equations and how to approach solving them effectively. Let's start by looking at the parts of a quadratic equation. The term a is the coefficient of x squared. We call this the quadratic coefficient because it's attached to the x squared term. Next, b is the coefficient of x, and this is known as the linear coefficient. It's called that because it's linked to the x term, which is linear. Then, c is the constant term, which is just a number without any variable attached. When we put it all together, the standard form of a quadratic equation looks like this: x squared plus bx plus c equals 0. Here, a, b, and c are real numbers, meaning they can be any real value, but with one important condition: a must not be 0. If a were 0, then we wouldn't have a quadratic equation anymore. It would just be linear. Understanding this standard form is essential because it's the foundation for analyzing and solving quadratic equations. It helps us identify the coefficients quickly and prepares us for graphing or solving the equations efficiently. Remember, the key points are the roles of a b and c, and the fact that it can't be 0, ensuring we're dealing with a true quadratic. Let's talk about the roots of a quadratic equation. As you can see, a quadratic can have different types of roots. It might have two distinct roots, meaning two different solutions, or it could have two equal roots, which happens when the parabola just touches the x-axis at one point. Sometimes, real roots may not exist at all, which means the parabola doesn't cross the x-axis. Now, if alpha is a root of the quadratic equation x2 plus bx plus c equals 0, that means when we substitute alpha into the equation, it satisfies it. So alpha 2 plus b alpha plus c equals 0. The values of that make the equation true are called the roots. Understanding these roots is fundamental because they tell us where the quadratic intersects or touches the x-axis, and they form the basis for methods to solve quadratic equations, like factoring, which we'll explore next. This concept ties into the overall theme of solving quadratics efficiently and understanding their graph behavior. Now, let's look at how we can find the roots of a quadratic equation by substituting the values of a, b, and c when we do this. We can directly calculate the roots without needing to factor the equation manually. The quadratic formula, which is x equals negative b plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a, gives us a straightforward way to find those roots. This formula is incredibly useful because it allows us to determine the solutions directly from the standard form of the quadratic equation, x squared plus bx plus c equals 0. So, in essence, the quadratic formula is a powerful tool that simplifies solving quadratic equations, especially when factoring is difficult or impossible. The discriminant is a key concept because it helps us understand the nature of the roots of a quadratic equation. It essentially tells us whether the roots are real or complex, and whether they are distinct or repeated. For a quadratic equation in the form x2 plus bx plus c equals 0, the discriminant is the expression b2 minus 4ac. This value is often denoted by the letter D. By examining the discriminant, we can quickly determine the characteristics of the roots without actually solving the equation. It connects directly to the overall theme of understanding quadratic equations more deeply, giving us insights into their behavior based on the coefficients. Let's explore the nature of roots based on the discriminant, D, which is calculated as b squared minus 4ac. This discriminant helps us understand what kind of roots the quadratic equation has. First, if d is less than 0, that means the quadratic has no real roots at all. In other words, the solutions are complex or imaginary numbers. Next, if d equals 0, the equation has two equal real roots. Sometimes we call these repeated roots because they are the same, indicating the parabola touches the x-axis at a single point. Finally, if d is greater than 0, then the quadratic has two distinct real roots. These are two different solutions, and the parabola crosses the x-axis at 2 points. Understanding these cases is crucial because it helps us predict the behavior of quadratic equations just by looking at the discriminant. It connects directly to the overall theme of analyzing quadratic functions and their solutions. Let's look at the given equation. X plus 1, 2 equals 2 times x minus 3. To understand this better, we'll use the expansion formula for a squared binomial, which is a plus b2 equals a 2 plus 2 ob plus b2. Applying that here, we get x2 plus 2 times x plus 1 equals 2x minus 6. Simplifying this, we see that x2 plus 2x plus 1 equals 2x minus 6. Subtracting 2x from both sides, we're left with x2 plus 1 equals minus 6. Adding 6 to both sides gives us x2 plus 7 equals 0. Now, notice that this is in the standard quadratic form x2 plus bx plus c equals 0. So in this case, our given equation is indeed a quadratic equation. Moving on to the solution, we start again from our original equation. X plus 1, 2 equals 2 times x minus 3. Next, we can manipulate the equation by rewriting 2 times x minus 3 as 2x minus 6. Alternatively, sometimes it's helpful to express the right side as a product involving negative 2, like minus 2 times 3 minus x, to see different perspectives. When we expand this, using the same binomial formula, we get x2 minus 2x equals negative 6 plus 2x. Bringing all terms to one side, we have x2 minus 2x plus 6 equals 0, which simplifies to x2 minus 4x plus 6 equals 0. Again, this is a quadratic form, confirming that the original equation leads us to a quadratic equation. Finally, it's important to check whether certain equations are quadratic. For example, in exercise 4.1, students are asked to identify if the equations presented are quadratic. Remember, quadratic equations are characterized by the highest power of the variable being 2, and they typically follow the form x2 plus bx plus c equals 0. Recognizing this helps us understand the structure of equations and their solutions better. Throughout this process, connecting the algebraic manipulation back to the form of the equations is key to mastering quadratic equations and their applications. Let's analyze this problem step by step. We are told that the product of two consecutive positive integers is 306. Our goal is to find these integers. First, I will assign a variable to the first integer, which we'll call x since the integers are consecutive. The next integer will simply be x plus 1. Now, the product of these two integers can be written as x multiplied by x plus 1. According to the problem, this product equals 306. So we write that as x times x plus 1 equals 306. Expanding this, we get x squared plus x equals 306. To set it up as a standard quadratic equation, we bring all terms to one side, giving us squared plus x minus 306 equals 0. This quadratic equation, x squared plus x minus 306 equals 0, is the mathematical representation of the problem. It captures the relationship between the two integers in an algebraic form. By solving this quadratic, we can find the value of x, and consequently, the two integers we're looking for. This approach illustrates how real-world problems involving consecutive numbers can be translated into algebraic equations for easier solving. Let's consider the problem carefully. Suppose John has X marbles initially. Then, since the total number of marbles they started with is 45, Givenchy must have 45 minus marbles. Now, after both of them lose 5 marbles each, John's remaining marbles become X minus 5, and Givenchy's become 45 minus X minus 5, which simplifies to 40 minus X. The problem states that the product of their marbles after losing 5 each is 124. So, we set up the equation. X5 times 40x equals 124. This is a key point because it turns the real-world situation into a mathematical problem. Solving this equation will help us find the initial number of marbles John and Givenchy each had. Remember, the goal here is to represent these situations mathematically, which helps us understand and solve the problem systematically. So, by translating the story into an algebraic equation, we've connected the real-life scenario to the mathematical tools we have, making problem-solving more manageable.